So this actually, don't worry about this not being recorded because this is just to summarize what we learned last class. Okay? And that's really big step. And this guy, and as you can see, the methanol can come over to take the proton away, okay? Give you the final product. And the red one, green one, okay? And obviously you get the. So in this kind of system, it's the concentration of methoxide, okay? In this acidic system, the concentration of methoxide is exceedingly low. So you can forget about the product produced by methoxide ion acting as a nucleophile. Because how do we know the methoxide ion concentration? You can cheat, okay? The methanol have the same acidity as water, similar. Okay, they are indeed very similar. So you can calculate if you need to form methoxide ion, okay? You have to using this equilibrium, okay, you can form methoxide ion. But this equilibrium, the K is about 10 to minus 16, okay? And then if it's acid catalyzed reaction, the proton concentration usually say 0.1 m, okay? Then this one concentration will be 10 to minus 15 m, okay? Roughly, okay? Roughly. So the concentration, this concentration is so low, so the end product can formed by the nucleophilic attack of methoxide, you can completely ignore it. It's like more than 10 orders of magnitude lower than the methanol. Okay, although methoxide is more nucleophilic than methanol, but the concentration is more than 10 orders of magnitude lower. So you can forget about the product formed by nucleophilic attack of methoxide. So this is a common rule. If it's acidic system, you can forget about those strongly basic species acting as nucleophile because their concentration are exceedingly low. If it's a basic system, you can forget about the acidic system, highly acidic species acting as electrophile. That's just a general consideration you should have. Anyway, so that is what we mainly learned in last class. Now the application, one application of the the acid catalyzed ring opening reaction of epoxide is that you can actually carry out the acid catalyzed hydration of epoxide. So let's say you have a cis epoxide as shown here, okay? And this cis epoxide could be formed by epoxidation of a cycloalkene. That's what we learn in Organic 1, Chapter 8, I believe. Okay? And then this epoxide, if react with water in the presence of acid catalyst. So this acid catalyst typically should be an acid that that is not nucleophilic. So what are examples of acid that are not nucleophilic other than this one? Can anyone tell me all that? Yes. Phosphoric acid. Okay, very good. That's one. Okay, and yes, sulfuric acid. Those are two most commonly seen non-nucleophilic acid. Yeah, this one also is very famous non-nucleophilic acid, but this one is not commonly used because it's a lot more expensive than these two guys. Okay, a lot more expensive. Okay? But anyway, so what you see is basically, okay, first thing is mechanistic. This one will be protonated. Whatever this one of those three atoms will be used, okay, will be protonated. That's the first. Then in the rate limiting step, the water will be acting as a nucleophile, and will attack one of the ring carbons. And such attack will be always, the SN2 style. Okay, so then because these two CO bonds should be wedge bonds, because the two CH bonds, they are dash bonds. Okay, so then if it's SN2 type attack, the nucleophile must be attacked from the opposite side of leaving group. So what is the leaving group here? No, which bond will be breaking? If you look at this reaction, which bond will be breaking? The CO bond. Okay, the CO bond. Okay, so it doesn't matter. We can treat. Let's say assume the lower this one CO bond will be breaking. Okay, so then the water will be coming from opposite side. So come from the below the ring. So from the direction of the dash CH bond. That's important because SN2 is type of attack. So if you see that the CO bond will be breaking, right? Assume this one will be attacked. Okay, CO bond will be breaking. Then the water must come from the bottom side, because the dash bond is the bottom, right, below the ring. Okay, so the water is coming from, will be attacking one of the two ring carbon from the direction below the ring. Okay, and that attack, when the attack happens, configuration inversion happens here at this carbon, but no configuration inversion happens on the carbon that's not attacked. Okay, so then what you get is this is a rate limiting step. You will get to this original dash bond. Okay, dash bond become wedge bond, CH. Okay, and then the water, okay, will be connect to the dash bond. So that's the SN2 type of attack. I hope you can see that. That's how SN2 work, because we assume this CO bond is the leaving group. Okay, is a breaking bond. Can you see my point? Hey, you can see it, right? So this bond is a breaking bond. Okay, is breaking bond. Well, we were leaving group. It's usually we say atom is leaving atom group leaving the electrophilic carbon. So O is leaving the electrophilic carbon. So yeah, it narrowly defined leaving group should be group leaving the molecular system. But if we wanted the term also apply to the say this kind of intermolecular SN2 type, not intermolecular. If it's a reopening system, we can say if the group or atom is leaving the electrophilic carbon, and the group of atoms leaving the electrophilic carbon is that O, right? Is leaving the electrophilic carbon. So we can treat that one as a leaving group. Okay. So and the top one, there's no change because the top atom is not being attacked. So that is intermediate. And then obviously water can come in to take one proton away from this intermediate. Okay? Then you get this product. Okay? So that is the called we call a dihydroxylation. This is a ring opening reaction of the epoxide, and when you do this kind of ring opening hydrolysis of epoxide, what you see, you will get a vicinal diol where the two OH group, they are trans vicinal diol. It's trans. So these two OH group, okay, they are opposite to each other, okay? Not opposite, they are on the opposite sides of the ring. One is above, the other is below, okay? So this is in sharp contrast with what we have seen in chapter what? 16, okay? If you do the osmium tetraoxide catalyzed dihydroxylation, you will get the cis diol. So this basically give you a choice, okay, to prepare, the both cis diol and the trans diol. So this will give you cis diol. But if you go through the epoxide, then treat using water. Yeah, if you treat the epoxide with water in acidic environment, you get a trans diol. So if you consider the epoxide is can be prepared from alkene, so this two-step process can be called anti-dihydroxylation. Basically, I install two hydroxy group on the CC double bond, original CC double bond, as the the two groups anti to each other. Okay, one OH above the ring, the other is below the ring. So this is called anti-dihydroxylation of alkene. And in chapter 16, we have seen that the syn dihydroxylation of alkene use osmium tetroxide as a catalyst. And the syn dihydroxylation give you cis diol, and the anti-dihydroxylation give you trans diol. Okay, so the mechanism different. Okay, so this is just it's a interesting way. No, they are basically provide us two interesting approaches can give us vicinal diols with different stereochemistry. One is a cis diol, one is trans diol. Any questions so far about this ring opening reaction of epoxide? If not, let's look at some epoxide in the biological process. So the epoxidation of alkenes depends on if you want to do it one step or two steps. If you want to one step, you can treat it with peroxy acid. If you want to do two step, that one is in the recorded video. You can first do the treat the alkene with halogen in water. Then treat that reaction. Treat the product mixture with base. So let's say if we have this alkene. If we treat it with bromine, water, okay, and what do we get? Vicinal halohydrin. So let's say we'll get OH, and then the Br, okay. This vicinal halohydrin. Then, if you treat this one with sodium hydroxide, okay, then you're gonna form the ring. So that is the two-step process of the epoxidation, and the product of epoxidation of alkene doesn't matter it's a single step or two step, you get the same kind of epoxide. But obviously, both epoxidation approach involve very reactive species. Peroxy acid is pretty oxidative, and this approach involves both pure halogen in its elementary form and a strong base. So in biological system, you cannot do, you don't have those strongly, basic or strongly oxidative species. And in biological system, epoxide can be formed by under the catalysis of enzyme, and then the oxidation agent is the most abundant oxidation agent on this earth, the oxygen, okay, in air, and then and also reducing agent NADH is involved in the reaction, to kind of supply the needed the hydride in the reaction system. So the net effect is the CC double bond can be epoxide, okay, using the combination of oxygen, NADH, and the proton. And then that's basically we're gonna complete all the reactions of all the discussions on preparation and reaction of ethers, and then let's spend a bit of time on the sulfur equivalent of ethers. Means in ether they are referred to those class of compounds with two hydrocarbon groups bound to the oxygen atom. Okay, that's called ether. Okay, and if we replace this O by S, then we get called sulfides. Okay, and the sulfide preparation usually done just like sulfur version of Williamson ether synthesis, and basically you're going to using a thiolate. It's a conjugated base of thiol react with alkyl halide, and this sulfur version of Williamson ether synthesis is actually it's more forgiving when it comes to what kind of alkyl halide you can use. And I hope you recall, what kind of alkyl halide you can use in a Williamson ether synthesis. What kind of alkyl halide? Yeah. Iodide certainly can use, but the major limitation is not what kind of halogen you use. Yes. Yes, you should be primary or even better, like a methyl. Okay. So basically the alkyl halide, the alkyl group must support SN2 reaction much better than the E2 reaction. Okay, that's the key part. So that's primary alkyl halide, or even better, methyl. So this is a limitation of Williamson ether synthesis. But now we are using a sulfur version of Williamson ether synthesis. So what's the difference between thiolate and alkoxide? What's the difference? If you compare and contrast the thiolate and alkoxide, so first, in terms of nucleophilicity, which one is better? The thiolate is better, about 10 to 100 times better. Nucleophilicity, okay? So that means thiolate will much more likely undergo SN2 reaction, okay? Because thiolate is 10 to 100 times more nucleophilic. That's what we discussed in Organic 1, Chapter 6. Then this is 1, so make thiolate favor SN2 better. Then second, the basicity. That's what we're talking about, which kind of chemical species will be more likely to undergo E2 reaction. Which was more basic? We talked about chapter 16. Thiolate and the alkoxide, which one is more basic? The alkoxide, because thiolate is about roughly about 6 orders of magnitude less basic than alkoxide. 6 orders of magnitude. So the alkoxide conjugate acid, ROH, pKa is about 16. Okay, but for thiol, SSH, usually around 10. Okay. So means what? Means alkoxide is much more likely undergo E2 reaction. So again, makes thiolate, the less likely undergo E2 reaction. So basically, compared to alkoxide, thiolate is first it's more nucleophilic. Second, it's less basic. So more likely go SN2, less likely go E2. So thiolate can perfectly accommodate secondary halide. Perfectly accommodate secondary halide. Okay, so that's what we have here. Even with secondary halide, okay, you treat a thiolate, no problem. Major product will be SN2 reaction product, the sulfide here. Okay, and in contrast, if you treat this one, okay, chloride, same chloride with methoxide, you will get essentially 100% elimination product, essentially 100%. Okay, not even 90%, 80%, essentially 100%. Why? Because this alkyl halide, okay, it's a secondary allelic alkyl halide. So not only it's even more. It has a stronger tendency to undergo E2 reaction compared to this one. So these two alkyl halides, okay, both are secondary, right? But this guy has an even stronger tendency to undergo E2 reaction than this one. Why? Again, look at the product. Why this alkyl halide has even stronger tendency to undergo E2 reaction than the one above it. I try to let you guys, encourage you guys, put all the, the knowledge about all topics together, make them, just make sense. Yes. Yes, because no, probably yes. Which one stable by resonance? Oh yeah, because this one is stabilized by conjugation, pi conjugation. Okay, so this one stabilized pi conjugation, and then in the transition state, you have a partially formed double bond. Okay, it's stabilized by conjugation. So that if the transition state is more stable, the reaction is faster. So that's why this guy is especially want to undergo E2 reaction, because that product is stabilized by conjugation. So let's just say if you guys just be more sensitive about possibility of have a conjugate structure, that will be more likely, to have. Okay. Anyway, so that's about sulfide. Then the sulfide is a little bit different from ether. They are, more likely to be oxidized. So if you recall, I think in the recall lecture we talked about ethers. They are kind of solvent. There's often have a safety issues related to it. Because of the ethers, both diester ether and THF, the two most common used ethers in chemistry lab, if we expose in air, they can gradually oxidize, slowly oxidize by air for peroxide. And those peroxides, they are explosive. Okay. So under those peroxides, their boiling point is higher than ether itself. So if you evaporate ether just a ether. Okay, if you have epoxide there during evaporation, the peroxide concentration will become higher and higher because ether evaporate away, and the peroxide product have a higher boiling point. They will remain in the flask, and then if you keep concentrate at one point, it will explode. Okay? So it's very careful for both diethyl ether and THF. If you're gonna work in a lab, they always there's a if you newly opened a bottle, write the date when it's open. Okay, then every half year you're supposed to check its peroxide level. So you don't want to, of course, you don't want to have explosion because I have not exact firsthand, but one of my classmates in college, when she was doing the evaporation of ether, at the end of the evaporation, explosion happened. And it's not a huge explosion, but the glass debris hurt her face. So still, it's very dangerous. So be careful when you deal with ether. But for ethers, those oxidation happens generally on the oxygen atom next to on the carbon atom next to oxygen. But the sulfide, they also can be oxidized, but the oxidation always happens on sulfur atom. So it's different from ethers. Why oxygen happens on the sulfur instead of carbon? And that is because the sulfur atom, okay, is more oxyphilic than carbon. Means that the sulfur can form very strong bond with oxygen atom. So although sulfur and the carbon both have essentially the same electron activity, but when it comes to directly bond with oxygen, sulfur often has a stronger tendency to bond with oxygen because it can form really strong bond with oxygen. So that's the reason when sulfide oxidized, you're gonna form SO double bonds. Okay, and really, whether you can have on sulfur, it can form one SO double bond or two SO double bonds, and you might see, oh, Professor, you are making a mistake. You are breaking the octet rule here and here. Okay, but it's not surprise. We break octet rule around the sulfur. We do it all the time. You remember sulfuric acid structure? I always break octet rule, okay? Because sulfur is a third period element. D orbital can be utilized, so it's okay. Okay. Now, the very last chapter is about the statistical analysis of ether, the epoxide, and the sulfide. So for the infrared about ethers is characterized by COC, the bond, means the two CO single bonds. Okay, if it's LQ ethers, CO single bond stretching should appear at 1100, okay, reciprocal centimeter. So what's the difference between ether and alcohol in terms of infrared spectrum? Let's say if I ask you what's the major difference you expect from methanol or ethanol and diethyl ether, what's the major difference you can expect? Ethanol and diethyl ether, what's the major difference? In terms of functional group, what's the major difference here? These two infrared spectrum. You're just missing OH bond for the diethyl ether. Everything else is the same. In real world, there may be some fine small difference, but in terms of functional groups, both have sp3ch, both of them have sp3co. As I said, only difference, ethanol one has a big, strong broad OH band, but the ether doesn't have it. Okay, so that's a major difference. And also, I want to show you some difference about the hybridization state of the ether carbons. Well, how it impacts the CO bond stretching frequency, and if the ether carbon, like here, this is ether carbon, is if it's sp2 hybridized, okay, then you expect this stretching, this CO single bond stretching frequency will go a bit higher. Generally will be above 1200 reciprocal centimeter. So if this is diphenyl ether, what you see, this is a CO stretching band, okay? And you see it's slightly above 1200. Okay, so this is 1200 mark, this 1200 mark, this is slightly above 1200, maybe 1230 something, okay, 1220, 1230 something, okay, it's actually 1237, okay. So this is a sp2 hybridized, you know, the CO single bond. Now, if it's sp3 hybridized CO single bond, generally around 1100 reciprocal centimeter. So this is dibutyl ether. Those two ether carbons, they are sp3 hybridized, so it's around 1100. So that's you know, the how the hybridization state carbon impact ether CO bond stretching frequency, just like alcohols. Okay, not much different here. Under the SO bond, in the sulfoxide and sulfur, they are stronger. You know, the depend on, you know, the how many, you know, the O you have on the sulfur. If it's you know, the single O on the sulfur called sulfoxide, the SO bond is about 1050. And if you have two of them, the frequency a bit higher. You have two of them around 1140 and 1300. You don't need to memorize this. Okay? The sulfurs are less commonly encountered. And the proton NMR of ethers, it's again, other than the OH proton, is the same as alcohol. So the ether, if you have a proton on the ether carbon, this proton will be deshielded in the same way as the, you know, the proton in alcohols, exactly the same. Okay, so the, you know, just like you know, like we look at here, this proton, those two protons, these two protons, okay. Those two let's say these protons, okay, and those protons, they are expected, the proton chemical shift is same range, about usually around 3.3, around that range, 3.3 to 3.5, okay, because those these protons, they are deshielded by, directly shielded by oxygen. Okay? And the similar proton in sulfide also will be deshielded, but the degree of deshielding is substantially lower than in alcohols, because after all, sulfur is less electronegative than the oxygen. So the only thing I also want to talk a bit is the epoxide proton. They are surprisingly, you know, the shielded. Means that if you look at here, those protons, okay, they are not between 3.2 to 4 ppm range. Those two protons, they are in about 2.5 ppm. So why that's the case? So those protons, they are about 2.5 ppm. That is because those CO bonds, okay, they are weaker than typical CO bonds because of the bond angle is far less than they want to be. So the, you know, the electrons, okay, they actually don't exactly stay, you know, this sigma bond electrons, they don't exactly stay, you know, the in between this oxygen, at the center of this oxygen and this carbon bond. If you really look at electron density, those electrons more likely stay here. Okay, the sigma electrons more likely stay here instead of what you expect for sigma electrons is supposed to be. the sigma electrons should be staying here, okay? But actually, it's the sigma electrons with these CO bonds able to going above the bond axis, CO bond axis, outside of the bond axis, okay? So that lead to, the electronic effect of this oxygen is not fully exercised on this carbon. If we know this, this proton, this proton is deshielded, okay, is because this proton, they are deshielded because of electron withdrawing effect of oxygen. Okay, but if the the electron with the chemical bond between the carbon and oxygen, is not as strong as typical chemical bond, then the electron withdrawing effect of the oxygen is not fully exercised on this carbon. So the epoxide protons, they are, surprisingly shielded, almost similar with the, the sulfide. And the carbon-13 of ethers, there's no surprise. The ether carbon is deshielded because of electron withdrawing effect of oxygen. Okay, and similarly, the sulfide carbon, they are also deshielded, but to a significantly less extent than the the ether carbons. Okay, here's the example of the carbon-13 NMR of dipropyl ether. So the obviously this peak, okay, this peak must come from the carbon that directly bound to the oxygen. So these two carbons, okay. Then the under the similar trend, you can, the similar story can be said from the others. This carbon must be come from the carbons a bit further away from the oxygen atom. And then the carbon at 10 ppm obviously is the one, really the end one, the methyl carbon. That's nothing new here, pretty much. Okay, so the mass spectrometry, the of ether and the sulfide, they can easily undergo fragmentations. Okay, so how do we analyze the the fragmentation of ethers? So you have to think about, if you want to remove electron from an ether molecule, where the electron should come from. And then that that electron must come from the electron that has the highest energy. So what kind of electron has the highest energy here in this ether molecule? What kind of electron has the highest energy? Not the bonding electron. The bonding electrons generally have low energy. They are stable. So if you have anti-bonding electrons, they will go first. And here we don't have anti-bonding electrons, so which electron we are looking at? We look at the non-bonding electrons. So what kind of electrons are non-bonding electrons? The lone pair. Okay. So if you take electron away, always going to take one of lone pair electron. That's like this one. Okay. Then you have this called cationic radical. Okay? The cationic radical generally have the same mass number as the molecule. This is a molecule. Basically, it's called molecular ion. But this molecular ion can easily undergo a fragmentation process. So the fragmentation process is basically will happen that give you a stable cation. So the fragmentation process here can happen in the two different ways. One is like here. Okay, I'm gonna move here. Okay, and then move this one here. Okay, and this one here. So this give you basically you cut this ethyl radical off. Okay, and give you this cation. Okay, this cation has a mass charge ratio 73, and I want to write this cation in probably the form you are more familiar with. You have this one, okay? This is a kind of a carbocation, right? You're more familiar with. But actually, the top form is more important because it has actual covalent bond. And because this just shows how oxygen lone pair can stabilize a positive charged carbon next to it, okay? And that's not the only way to undergo fragmentation process. The other fragmentation process can also happen, is basically instead of breaking off, the ethyl radical, you also can break off a methyl radical. So like, we do it here, okay, we do it here, do it here, okay. Then you can break off, we get a methyl radical. And again, this one you could write in the more familiar form to you guys. Give you this carbocation, okay? And obviously the bottom form is more important because it has an actual, the bond, okay? And this shows that, the lone pair bearing oxygen atom has very strong power to stabilize carbocation. Okay. So this basically concludes chapter 17. Any questions you might have? So the ether spectra, they are very similar to alcohols, just without the OH group. That's the key, just without the OH group. Now, if you don't have a question, we just look at chapter 17. That is in this 18, and this is a chapter we're gonna, the formally, the work with the star functional group of this of organic 2 carbonyl groups. Okay, we already seen this many times already, but this is a formal. We're gonna have a in detail discussion about carbonyl groups. Okay. So the in this chapter we're gonna be learning structural property relationship and some reactions of aldehydes and the ketones. And the aldehydes and the ketones, they are extremely common examples of carbonyl compounds. So the in this chapter we're gonna learn structural bonding of carbonyl group, and we will be looking at the many examples of nucleophilic addition as the typical reaction of carbonyls, and we will see examples of reactivity, and also we will see spectroscopic signatures of aldehydes and ketones. Because we are in a chapter specifically dealing with aldehydes and ketones, we will be learning more about spectroscopic property of aldehydes and ketones, especially infrared. Okay, because that's the spectroscopic technique you really use in organic 2 lab. Really use. Okay, others you don't really use at this point, right? At least maybe you might be giving spectra, but you don't really directly use the technique, other technique. But infrared is really going to use. Nomenclature only spend very little time on it because of my past experience with all the CSS students. You can learn this very well by reading itself because not much discussion, just set up rules, you apply them. So I guess just you guys can read it, okay? And I may test it briefly, but not much, as you know. Okay. So that's one common carbon, maybe 2 common, the aldehydes and or ketones. I would like you guys to know. One is acetone. That's probably mostly commonly used carbonyl compound. Okay, acetone. We could use IUPAC name, but this is so commonly used. Nobody uses IUPAC name for acetone, basically. The other ones are, the formaldehyde. This is also very, very commonly used carbonyl compound. especially in polymers. Okay? So you're gonna see formaldehyde in those plywoods, in adhesives. Okay? But they're not in its freestanding form. They are in compounded form. You're gonna see formaldehyde in composites, in plywood, in adhesives, a lot of things. Formaldehyde is very commonly used compound. Okay, and that are the two carbonyl compounds. I would strongly suggest to be familiar with the common name because those two compounds they will be referred to using their common name. They're just so commonly used, so IUPAC names no longer, no really nobody uses that. So the IUPAC name of this one technically is called methanol. Okay, this one IUPAC name, but formaldehyde. So seems everyone called it formaldehyde. Okay, but although it's official IUPAC name, we call methanol. Just that seems like nobody uses that. All right, then let's look at the structural bonding and the carbonyl groups because this analysis will help us, understand, the reactions of the carbonyl groups. Okay, yeah, I forgot E, aldehyde. Okay, E here, aldehyde. Okay, so a carbonyl group. Okay, without even knowing details, just look at this Lewis structure. By applying VS-EPR theory, we should know that the carbon must be what hybridization state for that carbon? sp2. How about the oxygen? How about oxygen? Oxygen, what is the hybridization state? sp2, yes, because also 3 groups of electrons around it. So both atoms are sp2 hybridized. So because sp2 hybridized, again, just combine with VS-EPR, so the bond angles around that carbon should be around 120. So yeah, they are pretty close. So we don't have to remember exact details as long as they're close to 120 will be sufficient. They are planar, close to 120. Okay? And then the other thing we want to look is we want to compare with the CO double bond with CC double bond because of obviously there's a lot of similarity between a CC double bond and a CO double bond. The similarities are both bonding non-hydrogen atoms. We're talking about carbon and oxygen. Both of them are sp2 hybridized. Okay, they have planar. They have one sigma bond and one pi bond. These are the same feature, right? Exactly same. Both have one sigma bond, one pi bond. Okay, and these are the similar thing. But what's different between these two guys? Other than that, the on the carbon, the CC double bond on the carbon, you have 2 additional bonds, but in CO double bond on the O, you have 2 lone pairs. Okay, that's pretty obvious. But I want to invite your attention to look at some, the quantitative aspects of these 2 bonds. You see the bond length of the CO double bond is noticeably shorter than a CC double bond. Okay, and if you measure the bond length, also a bond strength is also noticeably stronger than the CC double bond. So how much is stronger? Well, it looks like 10% stronger. Okay, and this is this is just a one double bond, but if you look at multiple CO double bond, CC double bond, yeah, CO double bond somewhere between 10%, 20% stronger, okay, than the CC double bond. So this actually is very, very important, okay, is that the CO double bond is noticeably stronger than CC double bond. So if a molecule is given the opportunity to either, okay, this molecule, okay, you have a choice, okay? The molecule was told, oh, you have a choice. You can form a CC double bond, or you can form a CO double bond. So what the molecule would like to form? Always CO double bond, almost, okay, with few exceptions, okay? Because molecules, they are very, materialized species, okay? Whatever makes them, more stable, they will go that path, okay? Unless it's rate limit, different story. That could happen, okay? Because the CO double bond is sizably stronger than CC double bond. So when there be a chance, the molecule in general would love to form CO double bond instead of CC double bond. That's something later will become important. Then the other thing, this does not show, this only shows the orbital. They are very similar, okay? Orbital. 1 sigma, 1 pi, bond, they are similar, okay? But if you look at charge distribution, then this, the two molecules, okay, will be quite, the different, okay? So the, CC double bond and CO double bond are quite different. And the CC double bond, as we know, in general, CC double bond itself is considered non-polar bond. CC double bond itself, because of the two carbons, okay, they have essentially same electron activity, okay. But a CO double bond, if you look at electrostatic map, you will see that there's a very large amount of positive charge on the carbonyl carbon. It's a purplish color, okay. Very large amount of positive charge on carbonyl carbon, okay. So this is kind of understandable. Basically, we know, the oxygen is second electronegative element. Carbon is the middle one, so there's a sizable dipole moment in the CO double bond, okay. And this, which is shown by this electrostatic map. And obviously on oxygen, there's a appreciable amount of negative charge, which is shown by the red color. And if you measure, the dipole moment of these two molecules, one called propanol, the other is called 1-butene. These two molecules, they are basically one is the alkene version, one is aldehyde version. These two guys, they have the essentially the same molecular weight, okay? So their property are more comparable. So you will see this this guy, okay, has an appreciably higher dipole moment because of it is can be, you can thank the high polarity of CO double bond. So now knowing that the CO double bond has the high dipole moment and the carbonyl being positive polarized, carbonyl carbon being positive polarized, and the carbonyl oxygen being negative polarized. So with this knowledge, now you should be able to predict the site of reaction if the carbonyl is subject to a reaction, okay? So if you throw in nucleophile into a carbonyl group, and the nucleophile, okay, could be anion, could be lone pairs, will be bound to the carbonyl carbon. Now, if you throw electrophile there, like what's the most common electrophile comes to your mind? Let's say if you ask electrophile, what's the most typical electrophile you know of? Just name one electrophile you know of. What carbon? It's reacting. It can be vary a lot. Depending. Oh, carbocation. Yeah, carbocation is kind of electrophile. Okay, but the carbocation, we usually look at from reagents. Okay? So let's say if you want to pick a reagent, you want to use an electrophile. So what's the most, let's say, what comes to your mind? If you want to say, okay, I want to pick a reagent, a chemical compound, okay? Not an intermediate, I pick a chemical compound. You want to use an electrophile. What comes to your mind? H3O plus, right? Okay, that's good. So if acid, just a proton, okay? Sulfuric acid, that's a classic example of the electrophile, okay? And basically proton Lewis acid. Those are, those will be reacting with carbonyl oxygen. So that's something helps you to think about where the site of reaction gonna be. So let's say if you have the this one, okay, if you throw in this one, which atom will be reacting with? Which atom it will directly, let's say, carbonyl carbon, carbonyl oxygen, which atom will be reacting with? Huh? Carbon, okay. Now, if I throw in this one, will be reacting with the oxygen because this Lewis acid. Okay? And then if you have this one, oxygen again, okay? And if it's this, oxygen or carbonyl carbon, both could be because water you can serve as a source of proton. It could also serve as nucleophile. So if you consider nucleophile, yeah, carbonyl carbon. But if you somehow serve as a proton source, that's carbonyl.
Because we have this reaction, how do you know which one will be the answer? It's going to be like two answers.
Which one is water?
Yeah.
Well, that depends on reaction time because water serves a dual role. It could serve as a proton supplier, could serve as nucleophile. So depending on what kind of function you have. If you consider nucleophile, yes, we will take it using the oxygen to attack carbonyl carbon. But if you it's a proton source, then the carbonyl oxygen. Okay. So that's how do you think about by this analysis, hopefully you can have a better view how carbonyl group can involve in reaction. Okay? And then because a carbonyl group can be involved in both a ketone or an aldehyde. So it will be interesting for us to compare, the stability of the ketone carbonyl and aldehyde carbonyl. So this comparison can be best illustrated by comparing this pair of isomers. And the top one is aldehyde, the bottom one is ketone. They are exactly, they have exact same molecular formula. So we can use heat of combustion values to see their stability. So what you can see, the aldehyde release a lot more heat. It's actually 33 kilojoule per mole heat than the ketone. And because the hydrocarbon chain is the same, so what you can say here is this carbonyl, okay, a ketone carbonyl is roughly 33 kilojoule per mole than the aldehyde carbonyl. So this is not so difficult to understand if you recall what we learned in organic 1. In organic 1, I hope you recall these two guys, okay? These two guys, they are alkene isomers, okay? They have different stabilities. And which one is more stable? The bottom one is more stable because of double bond is stabilized by more alkyl groups. So same argument can be applied here. And in ketone, the carbonyl group is stabilized by 2 alkyl groups. And the aldehyde, the carbonyl group stabilizes only 1 carbonyl group. So the more alkyl group can stabilize carbonyl group better. Okay. Only thing is I want to give you a quantitative comparison. So the largest difference, okay, in terms of in alkenes, monosubstitute alkenes, and the disubstitute alkenes, and the largest difference we see is these two guys, okay, right? This is a monosubstitute alkene. This is a disubstitute alkene, right? So largest difference across between a monosubstitute alkene and a disubstitute alkene is 17 kilojoules per mole. That's the largest stability difference. Okay, largest stability difference. Okay, and this only gives us 17 kilojoules per mole in stability difference, right? 17. You see that? 17. Okay, and but here we see how much? 33. Okay, so why this one is so much? It's almost double. Okay, the stability is double of what we have seen in alkenes. Okay, this can be justified, okay, by carbonyl group. Okay, because of this carbon, okay, is positive polarized, as we know, right? So this carbon is much more electron hungry than the carbon in the alkene. Okay? So because of the carbon is more electron hungry, so more alkyl group, each alkyl group has provided more stabilization. Okay? So this for this reason, the ketone have 2 alkyl groups. The additional alkyl group provides substantial greater stability enhancement than the alkenes because the carbonyl carbon is substantially more electron hungry, more electron deficient than the alkene, the double bonds. So that makes the additional alkyl group can give you greater stability difference compared what you have seen in alkenes. Okay, alkenes, look at here. Basically, this is a alkene. This is a alkene version. Okay, and this is the disubstitute alkene version, right? The largest difference you can get. Okay, and you would expect if the CO double bond, okay, is have the same hunger for electrons than CC double bond, the stability difference should be similar. But as we can see, the stability difference here is much more. It's how much more? It's like it's like the twice as much as the stability difference we see alkenes. So that's justified by the carbonyl group is much more electron hungry than the CC double bond. Now we also want using resonance description to analyze carbonyl group. So in addition to the normal normal Lewis form of carbonyl group, we can also write the polar form of carbonyl group. So out of these two, obviously this one makes greater contribution because of an extra covalent bond. But this one still makes a sizable contribution. And this resonance form can also help us to understand why nucleophile always attack a carbon and the electrophile always attack oxygen. Okay? And someone may say, okay, why I can't write the other one? Say, okay, I just want to do this, okay? So is this resonance form illegal? It's legal, not illegal. But the stability difference is, it's even CDA. Let's say if this one we consider 90% important, okay? This is a 9.9 importance. This one probably 0.1 importance, okay? Roughly, I'm not saying it's exact because of the left side resonance form is so unimportant because you are placing a positive charge on a more electronegative oxygen atom. It's very unreasonable, okay? But it's legal. Just say its contribution is so small you can ignore it. Okay? It's not illegal, just so bad. All right, maybe let's have a 5-minute break.